All right, so we're going to take a little bit of a turn here. We've been talking about acid and base reactions quite a bit. We're not going to be completely done with pH, all right, but we are going to kind of move on in our discussion of ionic equilibrium and talk about solubility products. Okay. So there was a little bit of a discussion of this topic last semester with regard to these precipitation reactions. All right, we'll revisit those a little bit, but let's just introduce some terminology that was thrown around. We said that an ionic compound, a solid, was soluble, meaning that that compound dissolves in water. Okay, or that compound was insoluble, meaning the compound does not dissolve in water. All right, and in Chem 1A, the world was kind of painted as this black and white thing. Things are either soluble or insoluble, and those are these hard, fast categories, all right? What we're going to learn today is this idea of being insoluble is never 100% true. Everything is always at least a little bit soluble in water. All right, you might not get a very large concentration of that ion produced, but nonetheless, there's going to be something, all right? And we're going to be talking about really teeny tiny quantities that usually we kind of ignore when they're that small. But when it comes to metals especially, even the smallest concentration of a metal can have kind of a big impact, especially in terms of us and our human biology. Arsenic, for example, we can only tolerate in a very, very, very tiny quantity before it's toxic to us. Lead is another example, right? We're very worried about our consumption of lead because our body can only tolerate a very tiny amount. So even trace amounts of these substances can be dangerous to us. All right, so we're going to be talking about things that are not incredibly soluble in water. You don't get very much at all. We're going to be talking in small quantities, but nonetheless, there's never anything that's 100% truly insoluble. All right, so let's remind ourselves of this sort of category of reaction that we had talked about, these precipitation reactions. All right. So, for example, silver ions and chloride ions in solution, they will find one another to create solid silver chloride. All right, we're going to spend a lot of time also looking at the reverse of these reactions here. Let's say instead of starting out with these two solutions we mix together, we're starting out with this solid silver chloride and we're adding it to water. These are what we call dissolution reactions. All right, now silver chloride was considered an insoluble compound, right? That means that this reaction here very strongly favors the products. All right, and so if this reaction above, our precipitation reaction, strongly favors the products, what can we say about our dissolution reaction? Does that strongly favor the products or the reactants? The reactants, right? Because it's literally just the exact reverse reaction. All right, cool. So first, we just kind of want to note that these reactions are closely tied together here, right? They are just simply the reverse of one another. And so what we're going to be looking at is the equilibrium between these reactions, all right? I'm going to kind of draw my arrows in this chapter a little weird. So let me just note, I'm going to be talking about equilibrium. So remember our equilibrium arrows kind of have these pointed in both directions to remind us that they're going in both directions, right? But wait, for this reaction here, because it strongly favors the products, I'm going to make that direction with my arrow longer than the other one. This is how we would represent a reaction that strongly favors our products here. Likewise, if I'm talking about my dissolution reaction, I want to do the exact opposite. I want to show that this reaction strongly favors the reactants. And we only get a little bit of product. All right, so again, we're kind of exploring how these two reactions are connected. We're going to look at their equilibrium. So let's build ourselves some equilibrium constants here. We're going to call this one up here the Kppt for precipitation. And this one is Ksp for solubility product. All right, so everybody take a second. Products over reactants, right? Give me the Kppt and the Ksp, and let's see how these are related to one another. All right, my products over my reactants, but what am I going to omit from this chemical equation? That's solid, exactly. So I'm just going to have 1 over the concentration of silver times the concentration of chloride. And for my Ksp, again, products over reactants, but now I'm going to omit that reactant. So it's concentration of silver times concentration of chloride. Right, so what is the relationship between these two here? My reaction is just reversed, so my equilibrium constants, these are just inverses of one another. My Kppt is simply 1 over my Ksp. All right, so if we know one of these, we know the other. Part of our constants page for this chapter is going to be a list of a bunch of different Ksp values. So listed here is, for example, aluminum hydroxide, one of our insoluble salts here. And what's listed is the equilibrium constant of that dissolution reaction. Okay, so let's look it up for this particular one. We got silver chloride, 1.77 times 10 to the negative 10 is our Ksp for that reaction. All right, so this reaction here, this Ksp value, 1.77 times 10 to the negative 10. What would we say about this reaction? It favors the products or the reactants given that value? Yeah, so reactants, it's less than 1, and it's way less than 1, right? 10 to the negative 10 is a tiny number. So yes, this reaction very strongly favors the reactants, which is kind of what we predicted anyway, right? That's why we drew the one arrow really big going towards the reactants and the other arrow really tiny going towards the products. Okay? Now we're going to use this KSP value quantitatively here. All right, so I want to know what is the concentration of silver if 10 grams of silver chloride is added to water. Okay, so we're going to need, we got our balanced chemical equation here for this dissolution reaction. We have our KSP expression. All right, and we're going to return to this strategy we've been using over and over again. First introduced actually to solve these equilibrium problems, those ice tables. All right. Now, first of all, real quick, let's think. Are we changing the volume? Are we doing a titration at all where we're combining volumes and all that? No. So we get to do our ice table in units of concentration. The other thing that we can note right off the bat that's going to make our lives a little easier is, do we see anywhere where those 10 grams of silver chloride are going to factor in to our equilibrium constant here? No. So it turns out, and we talked about this a little bit with Le Chatelier's principle as well, but it turns out because silver chloride is a solid, this calculation is going to be independent of the starting amount of silver chloride. We'll call it the initial amount. Of that solid. Oh, whoops. Ice table's down here. It's my KSP. All right, so let's build ourselves an ice table. Again, we looked up that KSP value, so we know that this is that 1.77 times 10 to the negative 10. All right, we don't have any of our product to start out with. What's my change box going to be? What's the sign of my change box going to be? Yeah, these are both products, so we're going to increase in their concentration. So at equilibrium, I'm going to have X amount of silver and X amount of chloride. And how are we going to figure out what that amount is? We're going to simply turn around and plug these back in to our KSP here, to our equilibrium expression. Right? X will get substituted in for the concentration of silver. X will be substituted in for the concentration of chloride. So I get my 1.77 times 10 to the negative 10 equals, I'm going to simplify, X times X is X squared. So then how can we solve for our value of X? We're just going to take the square root of both sides. right, I'm just going to say 3 sig figs here. So 1.33 times 10 to the negative 5 is my value for x. All right, remember we want to go and double check what our problem is asking for, which is the concentration of silver. And if I look on my ice table, the concentration of silver is indeed that value of x. Remember to always go back and check your ice table once we get done solving. So my concentration of silver is that value of x, or 1.33 times 10 to the negative 5. And what will my units be? Molarity. Cool. So we're going to take these relatively insoluble compounds, what we called insoluble, and we're going to add them to water, and we're going to calculate just how much they dissociate, just how many ions are formed. And is this a large concentration of ion that we have here? No, this is incredibly tiny. But again, that can be really super consequential, especially when we're talking about our metal ions. All right, cool. So let's see if we can do one all on our own here. All right. What is the concentration of barium when barium phosphate is added to water? This time I didn't even bother specifying an amount of barium phosphate because, again, it's going to be independent of that amount. All right, so give me a few things here. Our dissolution reaction. That equilibrium expression. And then fill it all in using that ice table. All right, so real quick, this dissolution reaction. All right, I have my barium phosphate solid being turned into these two aqueous ions. What am I missing here? My balancing, right? And I will tell you, this is going to be kind of the trickiest part of what we're going to be doing here today, is we've been working with chemical equations that were 1 to 1 to 1 for the past like 3 weeks now, all right? Both when you build your equilibrium expression and when you build your ice table, these coefficients are going to appear. And try to remind yourself of where these coefficients show up in our equilibrium expression as well as in our ice table. All right, I said these were going to show up in our equilibrium expression. I have my products multiplied together. My coefficients are going to become exponents. So barium will need to be cubed and phosphate will need to be squared in my equilibrium expression here. All right, my coefficients become exponents. And when I do my ice table, again, these are products, so I don't have any yet. I'm going to increase my concentration by some unknown amount. But for every barium phosphate that dissolves, I'm going to have 3 barium ions produced and 2 phosphate ions. So my stoichiometric coefficients will also appear in my ice table. All right, again, it's been a minute since we've been dealing with reactions that weren't simply 1 to 1 to 1. So remember, our coefficients will appear in our equilibrium expressions and our ice tables. All right, and when I plug this back into my KSP expression, right, I want to plug in my equilibrium concentration of barium and my equilibrium concentration of phosphate. Well, that concentration of barium is cubed, so when I put this into my KSP expression, I need to say 3x cubed, and make sure to put it in parentheses. That cube has to hit the 3 and the x, not just the x. Likewise, my 2x will go in parentheses here, squared. All right, so this becomes, I can take my 3 cubed times my 2 squared. It's 108. Yup. So I get 108. All right. And x cubed times x squared. What is that going to be? Cool, yeah. So remember, you add those exponents. Why is that? Always good to remember what it means to be cubed, right? That's x times x times x. Well, if we're going to multiply that by x squared, which is x times x, yeah, that's the same thing as x times x times x times x, or x to the 5th. So yes, in algebra, you would have learned that you add those exponents together. So 108x to the 5th. Okay. Cool. So what do we need before we can answer this? We need that actual value of KSP. So let's go to our constants page here. We're going to look it up for barium. Okay. Barium phosphate. There's a tiny one. 6 times 10 to the negative 39, and not a very soluble compound at all. All right, so how are we going to go about solving for x here? First, we needed to move that 108 over. All right, so now we have x to the 5th equals that 6 times 10 to the negative 39 divided by 108. All right, but how do we get rid of x to the 5th? We have to take the 5th roots of both sides. All right, so let me just show real quick. Our calculator. All right, how am I going to enter this in? Let's try to make it not so blurry. Oh, has it? Oh, it's true. That one's just fine. All right, my bad. Don't know. Try to fix that later. Sorry, y'all. Okay, well, direct your eyes to this one where you can actually see what's going on here. All right, I'm going to do 6 times 10 to the negative 39. I'm going to divide it by that 108. Let's start there. All right. In order to take a higher order root here, I'm going to have to use this button here above my x to the something box. Right? We see that there's a box above that square root sign. Now, I can't just hit it right away. Notice how it puts the answer up there above my exponent. Or above my root sign. That's not what I want. You have to enter the order first. So since I'm taking the 5th root, I'm going to say 5 and then hit that button. And now I'm taking the 5th root of that number. Okay? So I want to take the 5th root here. Boom. This illustrates another important problem of these that we're going to run into in this chapter because we're talking about such teeny tiny numbers. My calculator is just displaying this one digit, like it's really 0.9 times 10 to the negative 9th, or rather 9 times 10 to the negative 9th. Your calculator can only display a certain amount of digits, and then it just kind of truncates it, all right? So for this particular chapter, it's going to be important to display these numbers in scientific notation. So what I'm going to do is I'm going to go to mode up here, and I'm going to go down to not normal, but scientific notation, and hit enter. All right, now if I quit out of there and do that same calculation, it will display a bunch of digits here, the actual number written in scientific notation. Okay. The other thing that we can, in this case, we didn't really have to. Our algebra allowed us to simplify this. But the other thing that we can do and we're going to want to do in future problems is use our number solver. Right? So let me just clear my work here. If instead we just punch this into our number solver, 6 times 10 to the negative 39 equals 3x cubed times 2x squared. Again, we're going to get a tiny number for x, so we want to seed this thing with a tiny number here. All right, especially depending on how complicated the problem might be, it might take it a minute. But we see that it does indeed still arrive at that same answer. We just got to be careful again. If I display it in scientific notation, I get all my sig figs. If instead my mode was normal and I display my value of x, now it's going to truncate it again, right? So again, it's going to be important for not all of these, but for a lot of these problems to make sure that your calculator is in that scientific notation mode. So mode, go down and select sci. Cool. All right, so okay, we did our math. We got our value of x equals to that 8.89 times 10 to the negative 9. And we're done. No, okay, so again, we want to remember to go back and check our ICE table. The question is asking me for the concentration of barium. Well, according to my ICE table here, what is the concentration of barium? Yeah, not x, but 3x. So I'm close, just not quite there. My concentration of barium is equal to 3x, or whatever that is. All right, so 2 points, we'll do 3 sig figs again, 2.67 times 10 to the negative 8. And we're going to be good and include our units here. Again, it's been a while because we've been dealing with pH for forever, but what are our units going to be? Molarity. Cool. All right, so nothing too crazy here. These are really just equilibrium problems, but within the specific context of these insoluble compounds. All right, one of the tricky things we're going to have to remember is we're not going to see just one-to-one equations. So we got these stoichiometric coefficients. They're going to be exponents in our equilibrium expressions, and they're going to, and they're going to appear in the change box of our ice tables as well. All right, so now let's talk about the common ion effect. All right, so what is the common ion effect? The common ion effect tells us that insoluble compounds, like the silver chloride and the barium phosphate that we were just talking about, they are even less soluble in solutions containing a common ion. Yeah, exactly, right? So before we're going to prove this mathematically, but stole my punchline here. That's exactly what this is just an illustration of Le Chatelier's principle. Let's imagine that we took barium phosphate, and instead of sticking it in water, we stuck it in a solution that already has phosphate ions in it. Well, what happens if I crank up the concentration of one of my products? What does that have an effect on in terms of shifting this reaction? It's going to shift it even more in favor of our reactants, right? So that's exactly what we're going to do. We have a solution that contains a common ion, meaning one of the ions common to our compound here. And what we're going to see is this reaction is even less favorable then. It lies even more in favor of our reactants. All right, we're going to do so quantitatively though. So now we want to ask, what is the concentration of barium when barium phosphate is added to a solution that contains phosphate ions? We're going to say with a concentration of phosphate equal to 0.1 molar. All right, so we chose the same reaction, and so we'll have the same KSP expression. But now you're going to take a minute and fill in our ice table for these new conditions here. Right? We're not just starting with water that doesn't have any phosphate in it. Now we're starting with a solution that already contains those phosphate ions. Oh, whoops. All right, so my barium column stays the same, but now I do have an initial concentration of phosphate of 0.1 molar. And it's going to change by increasing by some unknown amount. And I got to factor in that stoichiometric coefficient of 2. So now at equilibrium, I'll have 0.1 plus 2x. And now I'm going to turn around just like before and substitute this back into our equation. So I get KSP equals 3x cubed times 0.1 plus 2x all squared. All right, please note that everything in green here is going to have to be hit by that exponent of 2. Okay, and honestly, we could use, x is going to be so freaking tiny, we could easily use our small x approximation, but for the sake of using our fancy calculators here, I guess we know this KSP value, right? That hasn't changed. It's a constant. 6 times 10 to the negative 39, 34, what was it? It was 39? Okay. That sounds so egregiously small. I was doubting myself. All right, cool. All right, so let's go ahead and try it out here. I got my 6 times 10 to the negative 39, same as before, equal to 3x cubed. But now I'm going to need to change this here to 0.1 plus 2 times x, all squared. Cool. I'm going to need to seed it with a tiny number. This is looking pretty tiny already, so I'm going to say, all right, let's do it. Pause for dramatic effect. All right, let's see, it kind of truncated it there in my display. So x, there we go, 2.811 times 10 to the negative 13. All right, now, let's be careful. I'm still not quite done with answering my problem here. I need my concentration of barium, which is 3x. So I'm going to take that value and multiply it by 3, or 8.43 times 10 to the negative 13. Okay, so let's kind of summarize here our common ion effect. We illustrated it with these two calculations here. In our first calculation, what we established was in water, the concentration of barium would be 2.6 times 10 to the negative 8. But in a solution with a common ion, That barium concentration is now 8.43 times 10 to the negative 13. And I was sloppy and didn't put my units. Molar. All right, and so what's the punchline here? We see we got a much smaller number, even less of that barium phosphate dissolved. Okay, and one other thing we're going to introduce here before we move on. I lost my page. There we go. Is what's called molar solubility. Your molar solubility is the number of moles of compound that will dissolve in 1 liter of water. All right, so when we were talking about silver chloride here, we said that we produced 1.33 times 10 to the negative 5 molar silver ions. Well, how many moles of silver chloride would have had to have dissolved per liter? Well, since this reaction is simply 1-to-1, it would just be that same value, that 1.33 times 10 to the negative 5 molar. All right? If we looked at another example here, we said that the amount of barium that we would get is 2.67 times 10 to the negative 8 molar. All right? But if we look carefully, we get 3 moles of barium for every 1 mole of barium phosphate that's produced. So the amount of moles of barium phosphate dissolved would be 1/3 of that amount, or just our original value of X. All right, so when you solve for your ice table, that value of X that you get is going to correspond to the number of moles of solid that dissolve, because we got a 1 out here, and we're always going to have a 1 for our solubility products. All right, so this molar solubility here, we can just make a note. This is the value of X when we solve that ice table. All right, and that tells us how many moles of our solid will dissolve in 1 liter of solution. Okay. Cool. All right, so we're going to sort of play a similar game here, but we're going to go to our solubility product table, and we're going to note that we see one common ion that we've talked about a whole lot in the past few weeks over and over and over again, and that is this hydroxide ion. All right, hydroxide is a strong base when it's paired with one of those group 1 metals, because then it's a completely soluble compound. All right? In the presence of most metals, hydroxide will actually form an insoluble precipitate. Now, we know that, let's take for example, we're going to look at magnesium hydroxide. All right, so let's just kind of start out our title or notes section here. All right, we want to look at hydroxide compounds. All right, according to that equilibrium constant, we know that that dissolution reaction does not happen to a huge degree, but nonetheless, it will happen at least a little bit, and any solution is really sensitive to changes in concentration of pH and pOH because of that log scale. All right, so we're going to basically ask a similar question, but not a little bit of a spin. What is the pH of the solution when magnesium hydroxide is added to water? All right, so let's get that dissolution reaction. Our KSP equation. And our ice table. All right, so I got my balanced dissolution reaction and my KSP expression. I'm going to build my ice table. All right, and this is where we got to be careful. All right, how much magnesium ions are there in pure water? 0. All right, but how many hydroxide ions are there in pure water? All right, so this is where we got to be careful, right? Because we have this auto-ionization relationship with water where it's always reacting with itself to produce hydronium and hydroxide. Normally, we get to just say this is 0 because it's such a small amount that we get to just ignore it altogether. But we're talking with really teeny tiny quantities here, right? I mean, our last solution was 10 to the negative 13 molar. So we got to pay attention to something that's present even in small quantities. What we are going to do is assume that our water that we're working with is neutral, and we want to work back to what we were talking about when we talked about pH ranges in our acid-base chapter. Okay? When we say something's neutral, that means that the concentration of hydronium equals the concentration of hydroxide. And remember, their product has to be 10 to the negative 14. So if they're equal to one another, that means that they are both at a concentration of 10 to the negative 7. All right? So we are starting out with some hydroxide in this solution, starting out with a concentration of 10 to the negative 7. All right, so our ice table here at equilibrium, we're going to have x and then 10 to the negative 7 plus 2x for our hydroxide concentration. What you're going to see is some compounds, depending on that value of KSP, you could easily ignore that 10 to the negative 7. Others, it makes a big, big difference. All right, so I'm going to teach you the one way that works every time here, which is we're going to make sure to include that in our ice table. All right, again, we're going to need to use our solver to help us solve this one. So everybody take a second and see if you can't do that on your own. I guess we need our KSP value. We looked at it before, but just to note again, in case we didn't write it down, magnesium hydroxide, 2.06 times 10 to the negative 13 is our KSP value. All right, and remember, I'm going to need to plug in for the concentration of hydroxide that 10 to the negative 7 plus 2x, which means that whole thing is going to be squared in my when I plug it into my equilibrium expression. Oh, sorry, hold on. All right, so I plugged it into my solver here. I got 3.727171 whatever times 10 to the negative 5. All right. Now, my question again, we're going to go back and read our question. My question's asking me for the pH. So what am I concerned about here concentration-wise to calculate pH? My hydroxide ion concentration. If I know that, I can calculate pH. And according to my ICE table, that hydroxide ion concentration is 10 to the negative 7 plus 2x or 7 point, we're going to just, again, round it to these 3 sig figs, 7.44 times 10 to the negative 5 molar. In order to get my pH then, I'm going to do 14 minus that POH, the negative log of my hydroxide concentration. Or 9.87. All right, so in no way is this a strong base, my magnesium hydroxide. Only a small amount of hydroxide was produced, but nonetheless, because these solutions are so sensitive to hydroxide concentration, that was enough to increase my pH, these 2.87 units. Cool. All right, so the last thing that we need to talk about with regard to our solubility products is what we call selective precipitation. All right, so what we're going to do is we're going to take a solution of 0.10 molar fluoride and 0.1 molar sulfide. So we have a mixture of these two anions, fluoride and sulfide. All right, we're going to take this solution and we're going to titrate in lead ions. All right, so let's first think about this here. What will occur? So now I'm not starting out with a solid and adding it to water. I have these ions in solution. So what are we going to expect to see here? Well, let's look at our table. If we find lead, it's in alphabetical order, so I passed it. There we go. We note that lead forms a lot of insoluble compounds. All right, one of which is lead fluoride, and the other of which is lead sulfide. So what's going to happen when we start titrating in those lead ions? What are we going to see? We're going to see this precipitate form. All right, and then what we're going to get to is which one's going to precipitate first. All right, but just in terms of what we see here, importantly, we're going to precipitate those insoluble solids. All right, lead sulfide and lead fluoride. Right? Lead will form an insoluble salt with both of those compounds. All right, but now let's ask, which anion, sulfide or fluoride, will precipitate first? All right, so I'm going to copy these entries over onto that other page. We got our lead fluoride. We got our lead sulfide. Okay. All right, cool. So we got these here. Let's see if we can't reason which one would precipitate first here. All right, reminder, these are our KSP values. And at the beginning, we talked about how we can just take the inverse to get our precipitate values, right? Our KPPT values. So let's do 1 divided by that KSP for each of these. This would be 3.07 times 10 to the positive 7. This would be 1.11 times 10 to the 28th. It's 3.03, sorry. I don't know where I got that from. All right, well, so according to these precipitation values, which one of these precipitation events is going to occur first? Which one is even more favorable towards the formation of that precipitate? My lead sulfide. Right, so which one will precipitate first? The one with the largest KPPT. And because of this inverse relationship, that implies it's the one with the smallest KSP. Which in this particular example would be that PBS. All right, but we can go a step further here. Great, so we know that that lead sulfide is going to precipitate first. Well, at what concentration of lead will that sulfide begin to precipitate? All right, yes, I know it's going to be the one that precipitates first, but how much lead do I have to titrate in before I'm going to see any solid form? All right. So we're going to need that relationship that we've been talking about to figure out our concentrations of our solubility product, that KSP expression. Let's first do our dissolution reaction. All right, I'll put that down real quick. This is a pretty easy one because it's 1-to-1. All right, I want you to build your KSP equation and see if you can't solve this one here. I'm going to give you a hint. You do not need an ice table for this one. All right, build that KSP equation and see what you got. All right, what we have is KSP equals the concentration of lead times the concentration of sulfide. So if I don't use an ice table, how am I supposed to figure out what this is here? Well, what do we definitely have from our constants page in this equation? The KSP value. What do we also have, though? All right, we have our KSP value. But what we also have from our problem is we know how much sulfide we're starting out with in this solution. We're starting out with that 0.1 molar. That was the premise of the problem. All right, we know how much sulfide ion is in there. So we have these 2 out of 3 variables. Let's just solve for that missing variable. All right, 9.04 times 10 to the negative 29. Divided by that sulfide concentration of 0.1 molar. All right, that's just going to bounce my decimal place over. So we get a concentration of lead equal to 9.04 times 10 to the negative 28 molar. Right, you don't need much lead at all, right? That's a very, very low concentration. Okay, so now everybody take a second. Let's ask for our other ion. Given what we just did here, everybody take a second and tell me what the concentration of lead will be when the fluoride ion starts to precipitate. All right, for the sake of time, I'm just going to say our KSP is that concentration of lead times the concentration of fluoride squared. Okay, again, I know my KSP value from my table, and I know my concentration of fluoride was 0.1 from my problem. So I'm just going to plug that in and rearrange to solve for our lead ion concentration. And we can see that our lead ion concentration would have to increase to 3.3 times 10 to the negative 6 molar, right? It's got to be a higher concentration than that of the sulfide, which checks out, because that's what we had said at the beginning, that our sulfide should be precipitating first. All right, but let's just note here, how is our concentration of lead going to get that high, right? Looking at this equation here, as we're adding in lead ions, our sulfide ions are binding together and we're forming that lead sulfide solid product, right? That means that my concentration of sulfide is going to be going down as this precipitation is occurring, which is going to allow my concentration of lead to increase. But importantly, the two of them are always still going to be tied together from this expression here. All right? So the last thing that I can ask you with regard to these selective precipitations would be, what is the concentration of sulfide when that fluoride begins to precipitate? All right, so what is my concentration of sulfide when fluoride begins to precipitate? Well, let's go with what we know our concentration of sulfide is linked to, and that is our KSP equation for that precipitation. So our KSP is equal to the concentration of lead times the concentration of sulfide. I know what that KSP value is. Do I know what the concentration of lead is when fluoride begins to precipitate? Yeah, right? That's what we just figured out before. So my concentration of lead will only be able to climb to this value if my concentration of sulfide has significantly decreased. And that's what we're going to calculate here, is what would that concentration of sulfide have to be? To the negative 29. All right, so rearranging and solving for our sulfide concentration, we get 2.74 times 10 to the negative 23 molar. Pretty much need it all gone before you're going to see any of that fluoride ion start to precipitate. All right, so importantly, these concentrations of lead and sulfide as well as lead and fluoride are tied together by these KSP expressions. So if we have a mixture of, in this case, fluoride ions and sulfide ions, and we start to titrate in, it's going to form these two insoluble precipitates, but it's not going to do so equally. One of them is going to form first. That's because we can see that our lead sulfide is way less soluble than our lead fluoride. that will begin to precipitate out at a very small concentration of lead. All right, our fluoride won't begin to precipitate until the concentration of lead reaches a little bit higher. And then we can figure out what the sulfide ion concentration would have to have decreased to in order for that lead to have gotten high enough for that fluoride to precipitate. All right, so these are our solubility products, all revolving around these insoluble compounds, right? Chem1A, we pretended like they didn't dissolve at all, and now what we're seeing is that they really don't very much at all, like don't get me wrong. But again, that can have a significant impact. Things like metal ion concentration is really sensitive to small concentrations. Things like pH are really sensitive to small changes in concentration. All right, so that's what our constants page here is going to be for. All right, I took 5 minutes extra of our time, so we'll start our lab at 35 after.